All right, I think we're recording. Yeah, it looks like we're in good shape. All right, welcome to day 23 of C and Software Tools class. We're almost a day behind in the lecture material, and I feel like I've been saying that for the last several lectures. I've been trying to catch us up a little bit. We've got, the semester is 1 day shorter than it would normally be, so we're not, even if we stayed on schedule, we wouldn't cover quite as much as we normally do. But I'll see how much I can catch us up, and that will affect how much C++ we get to talk about in the last few lectures of the semester. This is kind of where we left off last time. There were a few C features that we haven't needed yet, so we put those off until this late lecture. And we've had other ways of kind of getting around this or just not using a couple of these features. I mentioned this one at the end of lecture last time. C has an enumerated type, a way, just kind of like what Java provides, a way of defining your own type that has a limited set of values. And we've gotten by without this, and often people just use the preprocessor to do this kind of thing, to define names and map them each different name that could map to a different integer value. But if the compiler knew what we were trying to do here, it might be able to give us more useful debug or error messages. It might be able to catch places where we made mistakes using an enumerated type. And like I said, C does support this kind of thing. Was there a question? All right. And the syntax is a lot like, I think it's a lot like the Java syntax. It's a lot like the struct syntax in C. If you want to define your own enumerated type, there's a keyword enum that you can put in front. And then just like a struct, any name you want for that type can come after the enum. And then inside curly brackets, all of the values that that type is supposed to have. So here, I'm defining my own enumerated type. It just has 4 values in it: red, green, blue, and orange. And its name is, I called it color enum for the name of that enumerated type. If you define it like this, then just like a struct, you have to use that enum keyword whenever you want to talk about it. So here up at the top, I've defined a new enumerated type. But if I want to make a variable of that type, I've got to say enum and then the name of the type I just defined. And then, so here in the middle of the slide, I'm declaring a variable called myColor of the enumerated type I defined up at the top. And I'm giving it a value of green, one of the 4 values that I said this enumerated type can have. So this is, it's better than using the preprocessor to do this because, like I said, the language knows what you're trying to do. It knows that you're trying to define a type with a particular set of values. Once you've made a value of an enumerated type, what can you do with it? Well, a variable like myColor, or define another one down at the bottom of the slide, your color, you can assign it to any of the 4 values within that enumerated type. You can compare 2 enumerated values of an enumerated type, and they will be equal if they have the same value. So here I made one that's got red as its value and one that's got green. So those would, if you compared those with equality like I'm doing down at the bottom, they would not be equal. So you can test for equality. Often, just like with a struct, since defining an enumerated type gives you an enumerated type name. I feel like I'm saying the obvious. If you want to avoid having to say the word enum every time you want to use that type, people often use typedef to give a short name for the type. And just like with a struct, that's the reason that semicolon needs to be at the end, or it kind of shows that just like a struct, if you define a new enumerated type, you can start making instances of that type as part of the definition. So what I've got up at the top of my slide, I'm defining an enumerated type that has 4 values. And that direction at the end, that would normally be a variable of that type. But since I stuck the word typedef in front, Again, I think of a type def kind of like the same syntax as a variable declaration. So if I didn't have the word type def here, this would be declaring a variable named direction. But with the word type def here, I'm making an alias for that type. And then just like with struct, I can use that type name without having to say the word enum every time I want to use it. So people often do this. Here I'm declaring a new variable of this direction type, and I'm giving it one of these values. Now, Java has a fairly clever way of implementing enumerated types. Whenever you define an enumerated type, you're really defining a new class. And it only lets you make instances of that class that correspond to one of your enumerated values. So in Java, I think they figured out a really clever way of implementing enumerations. I'm getting a little bit old, but I think in the first version of Java that came out, enumerated types may not have been available, and that got added quickly after the Java language started being used. I made the point that Java has a clever way of doing this. C has a very obvious way of internally representing enumerated types. And you can see that at the bottom of the slide. Just like if we had implemented them ourselves using the preprocessor, an enumerated type in C is really just a wrapper around an integer value. And you can see this if you try to print them out. If you take here even this variable my direction that I made up at the top, and you print it out as an integer, that'll compile just fine. And the value you get corresponds to which of these names you use. Let me try to say an example, and that may be easier to understand than what I just said. When you make an enumerated type, the values of that type are really just words for integer values counting up from 0. So if you define an enumerated type like this, up is going to be just another name for 0, down is going to be another name for 1, left is going to be another name for 2, and right is going to be a name that gets mapped to 3 by the compiler. So that's why if I make a direction and I give it a value right, like I just said, up is 0, 1, 2, 3. So when you give this variable a value of right, it's really just storing the integer 3. And like I tried to say a moment ago, you can see this if you try to print out one of these values. It's really just a little decoration on top of an integer value. And you can even convert back and forth between those values. So if you take an enumerated type, the compiler will let you assign that to an integer variable if you want to use the integer value that the compiler is using to represent that enumerated value. You can even control this yourself if you want. When you define an enumerated type, you can use the syntax like I'm showing at the top of the slide. You can give a name and then equals and then some value. And that lets you pick whatever numeric value you want that each of those names are going to map to. If you specify a value, like for happy here, I said I want that to be represented with 2. If you specify a value, that's the value it's represented with. Otherwise, like for afraid, I didn't say what value that's going to be. It'll just keep counting up from the most recent value. So the example in the middle of the slide here, happy is going to be represented by 2, afraid will be represented by 3, the next value, the next numeric value, bored. I set that to 0, so bored is going to be 0. Blue for sad, I guess, is going to be represented by 1, again, counting up from the 0 I just said. Glad is going to be represented by 2, and this kind of shows that the enumerated values don't have to map to unique integers. Here, happy and glad are both going to map to, they're going to be different names for 2 when you're using this enumerated type. I mentioned that these are represented as integer values, and you can freely move back and forth between integer values and an enumerated type, including potentially overflowing. So at the bottom, I made a variable of this type. I started it out as happy. So that should internally be represented as 2. If I add 1 to that, then it's going to have the same value as afraid, because we said that's represented by 3. You can even overflow, or at least you can set the enumerated variable, a variable of enumerated type, so that it may not even correspond to any of the values of that type. So if I add 1 to it again, like I'm doing at the bottom, then it's going to internally have a value of 4, but that doesn't correspond to any of these names that I used up here. So we're kind of seeing that an enumeration in C is really just a thin wrapper around a integer value and the ability to pick names for various integer values. The scoping rules are just like any other variable declaration. So the compiler doesn't, for variables, you can't have 2 variables with the same name, at least not within the same scope. The compiler will complain about that. And the same is true for an enumeration. This is one reason I picked the word blue, because that is plausibly a mood, like we were using on the previous slide, or a color. But the compiler wouldn't let you define these 2 different enumerations in the same scope, because it would say, well, you've got blue here where it's going to mean 2. You've got blue here where its value is going to be 3. And the compiler won't let you have 2 different values for the same variable. If and the same here, it won't let you have 2 different values for that same name. Even if I rearranged these so that blue had the same value, it was maybe 2 in both of these definitions. If I moved it earlier in the second list, the compiler still isn't going to like that, because it's going to say you're giving me 2 definitions of the same thing, even if both of the definitions happen to agree. You can do the thing I'm showing down at the bottom. Just like declaring variables, the compiler will let you shadow a previous definition, as long as you do it at a different scope. So like I'm showing up in the middle of the slide, you can't have both of these declared at the same scope, because you'd have 2 different definitions of blue. But if you define them in different scopes, the compiler will let you do this. Enumerated values, like I've said, they are just, you can think of them as a thin wrapper around an integer. But the value of all of these enumeration values, red, green, blue, and orange up at the top, is considered a compile time constant. We called it a constant expression earlier, which means there are some places where this could be handy as a mechanism for defining your own compile time constants, as long as you just need integer values. And here I'm showing a place where you might want to do that kind of thing. If you were defining a struct for keeping up with a book, maybe you've got a couple of arrays. It's accidental, it's coincidence. This is kind of like what we did on Project 4 this semester. But let's say you needed space for storing a couple of strings as part of a book. But let's say you wanted that to be configurable, so you didn't want to hard code the size of the title or the author right there in the struct. You know, we could do this with the preprocessor. We could define a preprocessor macro that expands to whatever value you want. And then and this is what we've done for constants up till this point, and it's what we'll continue to do for constants. I'm just trying to show you another trick that some people do to define constants using an enumeration. The disadvantage of doing it the way we're doing it here is if we pick a name for size, then no one else can use that name because we've decided what it's going to expand to. If some other piece of code wanted to use a preprocessor constant named the same thing, the preprocessor is going to complain. It's going to say you're defining the same thing twice, because symbols defined with the preprocessor don't obey scoping rules. They're kind of like they all have global scope. But enumerations, we just said, these do respect the scoping rules. So you'll sometimes see people do what's called the enum hack. It is a way of defining constants as long as you only need integer constants that are compile time constants, but don't depend on using the preprocessor. So if I defined an enumeration, I could use that to store to keep up with a name for an integer value without needing to do this with the preprocessor. So instead of pound defining size to be 100, I could just make up an enumeration, and within that enumeration, I can pick any integer value for that constant. And since that's a compile time constant, I can use that to define things like array length. Why is this maybe better than using the preprocessor? That's what I'm showing at the bottom. I already mentioned the preprocessor doesn't respect scoping rules. So if you happen to use the same name for a constant as someone else, the compiler is going to complain about that. But enumerations do respect scoping rules. So you'll sometimes see people define an enumeration just as a way of keeping up with the name of constant. But if you use size to mean one thing in one struct and someone else uses it inside a different struct with a different value, the compiler isn't going to complain about that. This isn't what enum was made for, but this is a thing that people sometimes do with it. Again, because all the enumerated values are considered compile time constants. Questions? All right. So like I said, I'm filling in C features that we haven't talked about yet. There's one more thing. So we just did enumerations. There's one more way to define a type. And it's completely different from the kinds of things you can do in Java. And it's called a union. A union syntactically looks a lot like a struct. And that's why at the top of this slide, I'm saying, well, let's start from the idea of a struct. If you wanted to keep up with, here I'm pretending the example is storing contact information. So if you needed to be able to reach or find someone, maybe you could store an email address for that person, or a phone number for that person, or it's a silly example, but maybe GPS coordinates for where that person lives. Those would all be fine ways to keep up with a person, but you don't necessarily need them all at once. What if you needed to be able to store an email address or a phone number or global coordinates? If you define this as a struct, you get enough memory to store all of those. So you could put values in each of those fields. The struct stores all of its fields one after another in memory, potentially with some padding in between. A union, the syntax is almost the same as a struct, but instead of storing them one after another in memory, a union stores them all, like my picture tries to show, it stores them all within the same memory. A union is for making a storage that instead of storing all of its fields, it can store any one of its fields. So almost the same definition down here, but because I made it a union instead of a struct, the compiler is going to lay out the memory for this thing so that it can store either an email address or a phone number or two doubles for GPS coordinates. And like I'm trying to show in my picture, it stores each of those fields using the same memory. The size of the struct is going to depend on the largest field it has. So I said struct, the size of a union is going to depend on its largest field. When the compiler is figuring out how it's going to store this, it's going to make sure that it reserves for an instance of this union, it reserves enough memory for either an email address or a phone number or two doubles for GPS coordinates. But you can only use one of those at a time because they're all going to be stored. They're each going to be stored using the same memory. It's up to you, the programmer, to keep up with which field of a union you're using. So you can think of a union as a way of defining a data structure where instead of having enough room to store every one of its fields, you only need one of its fields at a time. And like I said, it's up to you, the programmer, to keep up with which one you're using. So up at the top of this slide, I made an instance of a union called Bill. And for Bill, I used its phone number field. So I'm storing, if we go back to the definition, phone number, I'm pretending we're going to store that as 3 short values. So each part of the phone number, I'll store in one element of that array. So for Bill, I fill in his phone number field. And then I made another instance of this union called Mary. But for Mary, I used the email address field. And you can see unions permit the same initialization syntax as a struct, but since you can only use one of the fields in a union, here I had to pick which of those 3 fields I wanted to fill in for Mary. So for her, I used her email address. And then you can access the fields of a union just like a struct. So for Bill, since I remember I set Bill's phone number up here, I can print that out like a phone number with 3 separate fields. For Mary, since I filled in her email address field, I can print that out as a string. But like I've said a couple of times, it's up to you to remember which of those fields you're using for that particular instance. So if I take Mary and I set up her email address, and then I try to access the phone number field, I'm going to be looking at that same memory. But if I stored a string in that memory, and then I try to access it as if it was 3 numbers, as if it was 3 short values, it's probably going to look like garbage. It's essentially going to be looking at the memory where that string is stored, but it's going to be looking at it interpreted as 3 short values here. Since it's up to you, since a union can only store one of its fields at a time, and it's up to you as the programmer to kind of remember which of those fields you're using for any instance of that union, this next slide shows how people would typically use a union. Normally a union would be part of a bigger data structure. So let's say you wanted to be able to store contact information for a list of people. You might take the union that we've just been looking at, the ability to store either a phone number or an email address or global coordinates, and you might make that whole union just part of a struct. So you can think of this last field, info, as being a way of storing any of those 3 things, email, phone, or GPS coordinates, but only one of them at a time. If you need other information to keep up with for contact information, like say a human readable name for the person you're storing contact information for, you could store that as a separate field in the struct. And since it's up to you to remember within a union which part of that union you're using, you could do this, you could keep up with that using an enumerated type. This would be a good job for what we saw at the start of this lecture. So here, in every instance of contact information, I keep up with a string of up to 19 characters storing a name. I've got an enumerated type that keeps up with, well, are you storing an email address, a phone number, or GPS coordinates for this person? And then my last field is the same union we've been using. It's where I'm actually going to store email address, phone number, or GPS coordinates. And then if you wanted a whole list of contact information, maybe for a list of people, you could, like I'm doing at the bottom, I make an array of this struct. For every element of that array, I can fill in the name field with a string. Every instance has, a member of this union. So within info, I can fill in either email address, phone number, or GPS coordinates. So that's what I'm doing in this last part. Every instance of this struct has a info field that's a union. So when I pick which field out of info I want to use, I'm using the same initialization syntax. Let me back up a slide. Same initialization syntax I was using here. I just put whichever field I want to initialize inside curly brackets. But since this union is part of a bigger struct, that's why this initialization is inside a value that I'm putting in this array. But since it's its own union, I put it inside an extra pair of curly brackets. And then this field in between the email field, I'm just picking a value for this enumerated type up here. So since for Mary, I'm storing her email address, I set this type field to remember, oh, for that person, I'm using the email address field. Yeah, and I think this is just a slide showing some of what I just talked about, explaining how I'm initializing this array. And every element gets, say it real fast, gets a string for the name, gets a value of this enumerated type for the type field, and then within the info field, you can use any one of the 3 fields defined by that struct. If you wanted to use a list of contact information like this, like here up at the top of this chunk of code, I'm pretending that I'm filling in an array with a bunch of contact information. And then if I wanted to print out the contents of that array, here I'm walking through every element of the array. But for some people, I'm storing phone number. For some people, I'm storing email address. If you wanted to print that out or compare it to something, then you're going to have to write code that looks at the, backing up a slide, that looks at this middle field and uses that to decide, well, for this element of the array, are you using the email address field? Are you using the phone number field, or using the GPS coordinates field? And that's what I'm doing right here for each element. I've got an if that says, if you're storing the phone number, print it out like a phone number. I didn't put all this code on the slide because it wouldn't fit, but we could write similar code to print out the email address if that's the part of the union we were using. This is how you would normally use a union. You can, just like we did with an enumerated type, whenever you use whenever you define a new union, if you want to use it, you have to use the union keyword. So, and I don't think I have a good example of code for what I'm talking about here, but just like with a struct, if you don't want to have to say the word union every time you make an instance of that union, you can use a type def to give it a short type name, like I'm doing up here. And then I define contact info as a union of these same 3 fields we've been talking about. Since I type def that union to this name contact info, if I want to use that now, I don't have to say the word union every time, because I've got a short name for talking about that type. And this works just fine, just like it would for a struct. We don't end up doing this as much because often, like I showed, a union is just, it's often used as a part of a bigger struct. And if that's the case, often you don't really need a type name for the union itself, because maybe the only place you're going to use that union is part of a bigger structure. And that's what I'm showing here. Same example we had before. I've got space for a name. I remember which part of the union I'm using an enumerated type. And then I've got the union itself. But let's say this is the only place I'm ever going to use that union. It's part of this contact info struct. And that union lets me store either an email address, a phone number with 3 parts, or 2 doubles for GPS coordinates. I could just define the union here and make a field of the struct info that has that union as its type. And notice I didn't even give a name for the type of this union, which means I can't talk about its type. I can't make other instances of that union elsewhere in my code because I didn't bother to give it a name. But here that would probably just be that would probably be just fine. The only place I'm probably going to use this union is when I'm talking about this field of this struct. So I went ahead and made a field named info. I didn't bother to give a name for the union type, again, because for this example, I'm probably never going to need that type outside of this struct. So this is what you'll typically see when people use a union. It's just part of a bigger struct. And the union itself may not even need a type name if you never need to use it outside that struct. I mentioned when I started talking about unions that this is something that Java doesn't have. I think it makes sense that Java doesn't support unions because using things or depending upon things like bytecode verification, Java has a much more strict type system than C does. Unions basically give you a way of saying, let me take this piece of memory and I'll back up so I can point to it. I want to define a union, which says reserve enough memory to store either an email address, a phone number, or GPS coordinates. And I want to be able to freely switch how I'm going to interpret that memory. If you say .email, you're accessing it as if it's a string. If you say .phone, you're accessing that same memory as if it's three shorts. If you access it using the .coords, you're taking that same memory and accessing it as if it's an array of two doubles. And Java would never let you do this. If you could take the same memory and kind of freely say, pretend this is an array of doubles or pretend this is a reference to an object, Java would not be able to do bytecode verification to make sure that programs aren't cheating, that they're not trying to access things that they shouldn't be able to access. If you had to do something like this in Java, I think you would use inheritance to solve this same problem. And in practice, that's how languages like Java do this. If you wanted, backing up a slide, if you wanted to be able to define contact information where you're storing either email address or phone number or coordinates, you'd probably make a superclass for contact information, and you would define 3 different subclasses of it. One of them also storing email address, one of them also storing phone number, a different one also storing global coordinates. And in languages like C++, that's typically how you would solve this same problem. C++ supports inheritance, much like Java does. These languages Java doesn't support stuff like unions. And in a language like C++, even though you still can use unions, this is much more, nowadays, this is done more often using inheritance, where each subclass can add different types of stuff. So that's why we seem to get by just fine in Java without a mechanism like unions. And even in C++, it's still there, even though it's probably not used as much as it used to be. I mentioned there were 2 other little things that we've gotten by just fine without needing these so far. But at least this first one is going to show up later in operating systems class. And it's one more storage class specification. It's the word volatile. Java also has volatile, just like in C. You haven't needed that in Java up to this point. But if you look at the list of reserved words in Java, it also has volatile as a reserved word. And it means almost the same thing in Java that it means in C. Volatile is a way of marking a variable, telling the compiler to that this variable might be changed by other code running on the same system that's not necessarily part of the code that the compiler is compiling right now. I did a terrible job of describing that, so I want to do over on that. Volatile is a hint to the compiler for how it should write code that accesses this variable. So here I'm defining a variable x. I marked it as volatile. And like I said, that's a hint to the compiler that whenever you're writing code that uses this variable x, the compiler needs to go directly to the memory where x is stored. It should not copy x to a register of the CPU. It shouldn't count on storing x as part of the operand stack in Java. It says whenever you want to get the variable x, or you want to modify the variable x, you need to go directly to the memory where X is stored instead of, again, instead of depending on holding a copy of X somewhere else. And the reason for this is the thing I said a moment ago. I just did a bad job of saying it. This is for variables that could be modified either by the hardware or other code running on the CPU, separate from the code that the compiler is compiling right now. So it's a hint that says, don't depend on storing a copy of X and then using that copy. You need to go, whenever you need to use X, you need to access the memory where X is stored. I've been trying to say this without using the word threads, but when we see this again in operating systems class, that's the reason words like volatile are available. Later in OS class, we'll start writing code that can be run, that can take advantage of multiple threads. And that just means we can write a program where it can be running in one subroutine, accessing some variables, and at the same time, maybe on a different CPU, other parts of our program could be running at the same time. And here, if both of those pieces of code are trying to access the variable X, they need to both agree to access it wherever it's stored in memory, rather than trying to hold a copy of X somewhere. So this, I'm mentioning it now because it is part of the C language, but until we start writing multi-threaded code, we won't really need to use this. But it's, as you'll see in OS class, it is awfully easy to write multi-threaded code either in Java or in C. And we'll start using this word in the class that comes after this one in typically operating systems class. So I probably spent too much time talking about volatile. There's one other designation that you can put on a variable, and it's the word restrict. And that is, you'll probably see this in some functions that are part of the standard library. Here I'm showing, if you look at the definition or the declaration of memcopy and memmove, it uses this restrict keyword. What does it mean? It is a hint to the compiler that says, for pointers, that says that two different pointers need to point to different regions of memory. As opposed to what? Well, you could have two different pointers that both point to different places in the same array. Restrict says, if you're taking two pointers, like if you've got a function that takes more than one pointer as a parameter, and you mark both of those pointers as restrict, or use this restrict keyword on them, that is a hint to the compiler that these two pointers need to be pointing to different locations in memory, not to just different parts of a bigger thing like an array. And a place where this is used is these two functions that we've already talked about. You remember memcopy and memmove, and they do almost the same thing. They copy from a source, any pointer you want to pass in, to a destination, and you just need to say how many bytes to copy. But you'll remember the difference between these two functions is memcopy only works if the source, it's only guaranteed to work if the source and destination don't overlap. Memmove is smart enough that it works even if the source and destination pointers overlap, or at least even if the region of memory you're copying, the source and destination regions might overlap. And you can see this documented in their use of restrict. And that's what I was trying to describe earlier in this slide. In memcopy, it only works if source and destination are non-overlapping regions of memory. And you can see if you look at the declaration of this function, both of these pointers are marked as restrict. For this function to work, they have to be pointing to different regions of memory. When the compiler is compiling the code for memcopy, having the guarantee that these two pointers are non-overlapping, or these two regions of memory are non-overlapping, could let the compiler write more efficient code for that. For memmove, Uh, we don't have to make that guarantee. The function is supposed to be smart enough that it'll work even if source and destination overlap. It won't start overriding the source as it's copying to destination, even if they do overlap. And you can see the definition here does not require those pointers to be restricted to point to different regions of memory. I mention it just to kind of round out all of the keywords of the language to try to make sure we've covered all of this. This will be something that you could use if you were defining your own function. It's mostly, again, a hint to the compiler that might let it write code more efficiently, as long as you can guarantee it that multiple pointers passed to a function are pointing to non-overlapping regions of memory. And that gets us to the end of what would have been day 22 in class. We're supposed to be on day 23, but we finished up this material kind of quickly, so we'll see how far we can get into our next batch of material. Questions before we move on to the lecture 23 material?
Do you know the difference between, like, if I was looking in one of the standard library headers, a lot of the restricts there use like double underscore restrict, double underscore. Is there a difference between those two, or are they like identical in function?
I would have to check. Here, I've got a shell prompt here. This is running on a Linux machine. Let's do man mem copy. It doesn't have the restrict here. Yeah, I'm sure. So I'd hoped when I brought up the man page for this that it would give us an example. I'll look into that. It might be kind of like when they introduced the bool type. They gave it a weird name, underscore big B bool, because no one was using that. And for restrict, that wasn't, I don't think that was in the original version of the language, so they added that later. And whenever they do that, they have to worry about, well, what if someone was using the word restrict in their code? We don't want to break that code. Off the top of my head, I don't know if that's the case for restrict. I'm pretty sure it wasn't in the original version of the language. And that may be why it is sometimes used with the double underscore in front. So my quick answer is, I'm not sure about that. That's my guess for why you're seeing that, but I'm not sure. Other questions? All right. So for day 23, what we're supposed to be talking about is kind of going back to the software tools part of this class. There are some things that the compiler, GCC, or compilers in general can do for you that we haven't talked about yet, or we haven't really needed them until now. But today we're going to talk about a few things that that the compiler can do for you that again, we haven't needed these until this point. I've listed these here. We'll start by talking about measuring code coverage. You probably did this in Java whenever you're thinking about testing your code. For white box testing, where you imagine that you want to write tests and the tests are written with some knowledge of what the source code looks like. One way to tell how good of a job you've done testing is to see how much of your code got executed under test. If you've got a program that's 1,000 lines long and you run tests on that, but only 100 of those 1,000 lines get executed, then you probably haven't done a very good job testing your code. There's a bunch of code that never actually got run under test. Whereas if you've got 1,000 lines of code and during test 999 of those lines did get executed, that gives you a reason to believe you've done a better job testing that. Almost every line of code at least got a chance to execute under test. That doesn't guarantee that there aren't bugs, but if you've got code that never actually got run under test, that makes it a lot easier for bugs to slip by. The way of measuring this is normally we depend on compile time tools, at least for a compiled language like C, that will compile our code with additional metering built in to measure things like which lines of code got executed under test, and even how many times they got executed under test. And GCC supports metering of your code for measuring coverage. You just have to ask it for that. We'll see, I'll go ahead and show you, it's on my next slide here. There are compile time options that tell GCC, when you're compiling this program, I want you to build in extra machine instructions, extra code to measure code coverage as I'm running it. And you can use this to measure, typically we think of measuring, using coverage measurement to figure out which statements got executed. But we'll see in a moment, you can measure coverage at an even finer granularity than that. If you've got a conditional in your program, if you've got an if statement with a conditional in that if statement, you can tell GCC to measure not only whether or not that if got executed and whether or not its body got executed, but which directions of branching in every conditional got executed under test. And for, if you've got some tricky conditional logic in your code, knowing how much of that condition got executed, kind of which way each individual branch went, can tell you a lot about can give you even more detail about how well you've exercised that code under test. So like I said, if we want to measure coverage, all we have to do is include some additional compile time options. And this will tell the compiler to build our executable with this extra metering built in. GCC supports this. We're going to use just these two. They're kind of long options, but -F profile arcs and -F test coverage will tell the compiler to execute our program with metering of code coverage built in. Once we've compiled our program like that, we can run it as normal. And it's going to run a little bit slower because it's got extra stuff built in. But every time we run it, the executable that got built this way will be measuring code coverage. It'll be paying attention to which lines got executed and which ones didn't. So that's what I'm trying to show at the bottom of this slide. We can run our program as normal, but if you look in the directory where your code is, you'll see that there are two additional files that are getting generated. This so I've got an example that does a bubble sort of a list of integer values. So that's why I'm pretending my program is called bubble here. We're going to go play with that in a moment. But when we compile that bubble program with backing up with these two options on the GCC line, the compiler is going to build this extra file, bubble.gcno. That you can think of as a map from the statements of your program, or at least, sorry, the machine instructions of your program back to statements of your source code. So the compiler, or when your program is executing, that keeps up with, well, this machine instruction that executes, what part of my source code does that correspond to? So that you can tell what lines of your code got executed and which ones maybe didn't. And this other file, bubble.gcda, keeps up with, gets updated every time you run the program. That keeps up with which machine instructions did get executed and which ones didn't, and how many times they got executed. Both of these files are in a binary format. So if you tried to look at either of these using a text editor, they'd probably look like garbage. There's a program, gcov, that interprets or that turns these two files into something that's human readable. And down at the bottom, I'm showing how you run that. Gcov, if you run it on your source file, it'll create a text file that shows how much of that source got executed and what parts didn't. And we're going to try this example in just a moment. But when we look at, sorry, I probably halfway said this. If you run gcov on your source file, it'll build a new text file that's got the same name as your source file, but with a .gcov at the end. And if you look in that file, it'll show you all of your source. It'll tell you what line of code each line of your source is. And over on the left, it'll show how many times each of those lines got executed. So here in the slides, I was talking through the example we're about to try out. So if you look at the posted examples for today, there should be source code for bubble.c. This is a simple bubble sort program. It reads in a list of integers and then it runs bubble sort on that. And then it prints out the list of integers, hopefully in sorted order. If you look down at main, on the stack, I make space for 25,000 integers. I call read list, that reads in integers from standard input into this array. Here's where my bubble sort is, I call sort list. And then when I'm done, print list prints it out, like I said, hopefully in sorted order at this point. Let's take a quick look at these three functions. Print list, it's right here, so we'll talk about it. You give me a list, a pointer to the start of an array in memory. You tell me how many elements are in that array, and it just has a for loop that goes through each element, printing out the value of them with a space in between. It prints them all out on the same line, so it puts a \n at the end of that line once it's done printing that. Let's go up to read list. So read list, we make it easy for the program by first telling it how many values we're going to input, and then we give it a list of values to sort. So it first tries to read how many values have to be sorted. It then reads all those values, and when you call it, you have to give it a pointer to the start of an array, and it returns the number of items it successfully read. So nothing too fancy here. You can see if anything goes wrong, I've got a little error function that gets called. That's up here at the top. It just prints out whatever error message you pass to it and then exits unsuccessfully. And then I think the only thing we have left to look at is our bubble sort. You remember how bubble sort works. It goes through the array over and over, looking at adjacent elements. And if it ever finds two elements that are out of order, it swaps them. So it's, as you probably know, it's not an efficient sort. Going through the array, swapping adjacent elements that are out of order, that's a linear time operation. But once you do that, the array isn't guaranteed to be in sorted order. All you did was rearrange adjacent items that are out of order. So you have to make multiple passes through the array to guarantee that it's in sorted order. If the array has n items in it, then you might have to make, well, I'll informally say up to about n passes through the array to guarantee that it's in sorted order. But if you ever make a pass through the array and you don't actually exchange two items, then you know that you're never going to exchange items. If they were all, if you never had to swap two items, then you're done. You're never going to need to swap items on a later iteration. So that's what this done flag is doing. I've implemented an early termination test on the bubble sort. And like I tried to say a moment ago, if you ever make a pass through the whole array and don't actually have to exchange two items, then you're guaranteed it's in sorted order. So I use this done flag to detect when that happens, so I can bail out early if I don't actually have to exchange items. There's a bug in this code. It's not a terrible bug. I've described it. I've got a typo here. I described it in this comment here, but for now we'll just ignore that bug because I want to use coverage measurement to help us detect that bug in a moment. All right, so we said if you want to compile this with support for code coverage, GCC, same options we've always used, -wall, -std equals C99. Let's turn on support for debugging with symbols, but let's use those two options we just talked about, F profile arcs, -F test coverage. Hope I got those right. And then the rest of it is what you normally have. Let's compile bubble.c and let's write out an executable bubble. All right, so I think I must have gotten the options right because the compiler didn't complain. I got a new executable for my bubble sort. That's this bubble right here. And that file I mentioned a moment ago, .gcno, that's the map from machine instructions to lines of source code. We can take a look at it, but like I said, it's sorry, I'm making mistakes using my editor. Bubble.gcno. And you can see it's a binary format. We can catch some strings in there, but it's mostly, we're going to need a tool like gcov to make sense of this file. Now we've got executable built to measure coverage. We just, we can run it as normal, but every time we run it, it's keeping up with which lines of code got executed and which ones didn't. And we'll be able to take a look at that later. I've got a input file, small input here that I'm going to test it with. It's in the format we just talked about. It's got 5 values in it. The first one, the first line of the file says, here come 5 values. And then after that are 5 numbers that get put in an array and sorted. So let's run bubble. So like I said, we can run it normally. It's trying to read from standard input, but I'll redirect its input from this small input file. There's the list of values now in sorted order. And if you take a look, this file .gcda got written out. And every time I run this program, if I ran it more than once, that file will get updated with additional coverage. So when you're testing a program, you might run it on a bunch of different test cases, and that file would get updated every time you ran it, keeping up with every line that got executed under any of those tests. We could take a look at that file, but like we saw with the .gcno, it's in a binary format, so it's not, we're not going to be able to make sense of it just looking at it in an editor. But we said gcov is a shell command that will interpret those 2 files and will show you coverage in a human readable format. It just wants the name of the source file that you want to see coverage for. And just like in our slides, it said, I was looking at bubble.c. That file had 36 lines in it. And if you look at the source code, it's more than 36 lines long. But a lot of those were blank lines or were comments or were includes. Of all of those lines, 36 of them represented things that you could execute. And of those, you covered about 2/3 of them. So about 2/3 of those lines got executed. So I would say we haven't done a great job testing this program yet, because there's maybe a dozen lines that we could have executed, but they didn't actually get executed under test. If you look at the file it generated, bubble.c.gcov, that is human readable, and it'll show you which lines in particular got executed. And I showed you this in the slides. This over here is all of my source code. Here's the line of the source code. So this comment was line 1. These includes were lines 3, 4, and 5. I had a function called swap, but I never actually called it. These 5 pound signs over here indicate lines that could have been executed under test, but they didn't actually get executed. The dash, that corresponds to a line of your code that wasn't even executable, like a blank line here. You couldn't, or there wasn't any code that compiled to. These includes, well, they didn't actually define any code, they just defined types. So they're marked with a dash to show you don't have to worry about executing that line. You couldn't have executed it. These 5 pound signs, those are your targets for improving your coverage. Those are lines, like I said, that could have been executed, but that didn't actually get executed under test. And there's one more example down here. If there's just a number over on the left, that's how many times that line got executed under test, or at least since the .gcda file got created. So you can see this if, or this assignment of done to false got executed once. This for loop got executed twice, or at least code on that line got executed twice. We already saw we never actually swapped two values. So this call to swap could have been executed, but it didn't actually get executed under test. So we should, I guess if we were trying to get good coverage, if we were trying to show that we had plausibly done a good job testing this, we want to throw in some other tests to try to make sure we hit these lines. So let's give that a try. We've already compiled the program. We don't have to recompile it, but we can execute it more times to try to make sure we increase our coverage numbers, to make sure that those statements that hadn't been executed get a chance to execute. And I deliberately didn't show you this file a moment ago, but I wanted to hide the fact that I deliberately made up a bad test for this program. This is the input I just ran it on. And the first line says, I'm going to give you 5 numbers. And then these next 5 lines, those are the numbers that this program has to sort. And you can see, yeah, that's a bad test case for a sort, because the input's already in sorted order. So we never actually had to swap 2 values because there were never any values out of order. But if we wanted to try to do a better job of testing this, we could just make up our own input. I'm going to go ahead and run this same program, Bubble, but instead of reading its input from a file, I'm just going to type it in myself. So probably a better test would be, let's do 5 numbers again. So I'm going to give you 5 input values: 75, -20, 3, 108, 91. And I'm just making these up, but I deliberately picked values that weren't already in sorted order. The output looks correct. They look like they're in sorted order, but let's see if that improved our coverage. So we'll run the same gcov command, but now it's going to reflect all the statements that got executed a moment ago when we ran it up here, and the test we just did on it. And you can see, well, we're not at 100%. Of the 36 lines, now we've run 86 points. We've run a little better than 80% of the lines, a little better than 85%. Let's take a look at this gcov report. So I just regenerated this file, and you can see, well, now the swap function did get called. Looks like it got called 3 times. So every statement in the swap function got called. This error function never got called. So if we wanted to do a better job covering this code, we should make up some test cases that force this to get called. Same kind of thing down here in read list. Well, the 2 statements where you call that error checking function or that error report function, those never got executed. We're doing a better job executing code in this. This is our bubble sort. So because we gave it a more interesting input, this code is having to do something now. And it looks like, yeah, it looks like the error reporting function is the only one, or the error handling code is the only one that, the only code that isn't getting executed. That's often, sometimes it's hard to test the error handling code, but here I think it's going to be easy. We just need to give some invalid inputs. So I'll run the program again. And here I'm trying to make the point that every time I run it, I'm accumulating additional coverage. So if this time I can manage to run that error checking code, my coverage will get updated with to reflect any additional lines of code that I execute. So thinking about the source code we looked at before, we had a test to make sure every value that gets put in is valid. And we even had a test to make sure the thing that the user types in that says how many values they're about to enter. We had a test to make sure that wasn't garbage. So let's try to execute that first one. Instead of typing in a number for how many values I'm about to enter, I'll just type in garbage. I got an error message, and this probably is going to help with my coverage. Let's run it again, but instead of typing a bad number, let's say I'm going to give you 1,000 inputs, and the first one is 5, the next one is 55, the next one is 555, and the next one is garbage. And this should exercise that other error detection case. And now real fast, if we rerun gcov, you can see now we are up to 100%. We've managed to test our code so that every line of code got a chance to execute. And we won't spend much time on this, but now if you look at the coverage report, you can see we executed this error handling function twice, once for each of the tests. And if you look down to the read list, the calls to that also got executed. So coverage is probably like you've done in at least one of your Java classes. It's a good way of trying to demonstrate that you've done a good job testing your code, showing that at least every line of your program had a chance to execute under test. What we've been looking at is kind of a coarse-grained way of looking at the coverage report, just looking at a line at a time. Whenever we ran this program, gcov is actually measuring some additional information. And this is what I mentioned before. It's looking at every conditional in your program. And like if you've got an if statement and a conditional inside the if, that condition could evaluate to either true or false. And if you want to convince yourself you've done a good job testing your code, you might want some tests where every condition has a chance to go either way. Otherwise, how do you know that you wrote the conditional exactly right? For more complicated conditionals, if they're built up of multiple tests, like with an and or an or between them, you might want to convince yourself that every part of that condition not only had a chance to execute, but had a chance to evaluate to true or false. gcov has been checking that kind of thing every time we ran our program. We just haven't been looking at it in the output. But if you run gcov and you put a -b on the option, or a -b option when you run it, you will get a report of all the branches in your program. And like I was trying to say, this can help you try to see if you've done a good job testing your conditionals. And you can see of the 36 lines of code, I had 18 conditions that got tested, but they didn't all get a chance to evaluate to true or false. There's one, and so this is a coverage report for the parts of your conditionals. And I'm not quite at 100 there. There's one conditional in this code that never got a chance to execute, or never got a chance to evaluate to both true and false. And now if we take a look at the coverage report, yeah, so I'm just trying to show you, the report got a little uglier because now it's giving us this branch information. Here's an if statement where we're checking the validity of each value that we read into our list. This if statement has a conditional, and the conditional could have evaluated to true or false. If it evaluated to true, which would mean the input had an error in it, scanf didn't return 1, then we're going to execute this. And of all the times we executed this conditional, 93% of them jumped past this this call to this error handling function. 7% of them, so really just once, it called the error function. So this conditional got a chance to go either way when it got executed. Right here is a more complicated conditional. This is essentially it's our outer loop in our bubble sort. And it's the piece of code that tries to keep running bubble sort until either we've run it enough times to guarantee our list is sorted, or that early termination condition. We ran it and we never actually had to exchange 2 values, so we can stop at this point without running additional passes through the list. And you can see right here is why our branch coverage is not at 100%. These 2 lines are telling us, well, of this first part of the conditional, keep running as long as you're not done, as long as you haven't hit the early termination condition. 60% of the time, this ran another iteration of the loop. 40% of the time, this got us out of our loop early. This other part of our condition never branched, never got us out of the loop early, or never caused the loop to terminate. So if we wanted to do a better job of testing this, it seems like we would want to give it inputs so that both parts of this conditional had a chance to do their job. I'm going to run the program one more time. I'll just type in some input, bubble. Let's say I'm going to give you 5 values, and let's give it values opposite of sorted order. So let's go 100, and then 90, and then 80, and then 70, and then 60. So completely backward from sorted order. And that should force the sort to have to swap a bunch of items to get the list in sorted order. You can see the output shows that it's in sorted order, but if we look at our coverage report, you can see we still didn't hit 100% on our branch coverage. If we take a look at the report, well, it's still that one part of the condition on that for loop that we never exercised. So this keep running iterations until as long as I is less than the number of items on your list. And that never got us out of the loop. We always got out of the loop because of this done flag, even though we just gave it a list that was completely out of order. And the reason for that is there's a bug right here. This is, informally, I said, if you're doing bubble sort, you have to take passes through the list, swapping items that are out of order until either you don't have to swap anything, that's what this first part does, or you've taken enough passes. And that's what this part of the condition does, but this part is wrong. I've written this loop so that it has to take at most n passes through the list, but that's one too many. If your list has n items in it, then you really only need to take n-1 passes through the list, and then you're guaranteed it's in sorted order. So because we were never able to get this part of the condition to do its job, it was never the reason we terminated this loop, I would say that helped us find an error in this condition. We're still guaranteed to get a list that's in sorted order. It's just this part of the condition is going to make us take, could make us take an extra pass through the list, even though it's guaranteed to be in sorted order. So here I'm trying to show that just having parts of your condition that you're never able to execute can help you detect bugs in your code. And here, well, you can see from my comment, I deliberately put this, wrote this bug into the code so that we could catch it by looking at coverage. We just got a couple of minutes left. Let's catch up. So I probably made that example take longer than it needed to. This is what we just did in that example. So we made sense of the coverage report. This is what I told you when I talked about reading the output of gcov. This is what we did when we asked gcov to give us branch coverage rather than just which lines of code got executed and which ones didn't. This is a prettier version of the code that we were just looking at, trying to make sense of gcov's report for which parts of our condition got to do their job under test. And that's all I've got to say about coverage for now. We're going to look at some compile time tools for measuring the performance of our code, with the idea that if we've got some performance critical code, it would be nice to have help from compile time tools to help us figure out where to concentrate our efforts in making that code more efficient. Trying to make your code as efficient as possible, I listed here some standard things that you might want to try. Your coding style, the way you write particular loops and things like that can have a lot to do with how efficient that code is. Certainly your choice of programming language. A language like C is made with performance as one of the main concerns. So programming in C could let you write much more efficient code than if you were programming in Java or Python or something like that. The way you run the compiler, the options you pass to it can have a lot to do with performance. But you can tell by my font choice here, all of that stuff tends to be insignificant compared to your choice of algorithm. If you're using an inefficient algorithm in some of the performance critical parts of your code, replacing it with a more efficient algorithm can make way more difference than either of those first three items. And that's why I picked bubble sort as our example before. I mentioned, well, bubble sort works, it'll get your list in sorted order, but it is an inefficient way to do a sort. And we didn't look at this example, but we'll do this next time we meet in class. We've been sorting tiny lists, list of 5 items. But I got a bigger list. It's called big input, and it's got 20,000 items in it. And that's not a huge number of items, but it's enough to show that bubble sort is a bad way of doing sorting. And it won't take a huge amount of time, but it'll take longer than it should to sort this list of 20,000 items. The tools that we're going to look at next will help us look at how fast our code is running and kind of look at what parts of it are generating the most overhead. But I've used up all my time for today, so we'll pick this up at the start of next week. Thanks for your attention. As usual, hang around if you have questions. And I know some people are wanting to ask some questions about the project, and that's fine too.